Welcome to this explainer. Today we're going to break down a pretty fascinating real-world math mystery straight from our source material. It's called Example 4.23, or as I like to call it, the flight sum. I am absolutely thrilled to take you through this one, mostly because it perfectly shows how these high-level math concepts apply directly to our everyday physical world. We're going to see how abstract numbers completely transform into very real physical distances.
Okay, so imagine this scenario. Two planes leave an airport at the exact same time, but they're heading in entirely different directions. Fast forward an hour and a half, where are they now? And more importantly, exactly how much empty sky is sitting between them? Now, right off the bat, that sounds like a job for a super complex radar system, right? But as you'll see, it's actually just a job for some foundational geometry. Part 1. Setting up the flight problem. Let's dive right into the data.
So here's the raw data we're working with from the source. We've got plane 1 heading due north at a blistering speed of 1,000 kilometers per hour. Meanwhile, plane 2 is heading due west, moving even faster, clocking in at 1,200 kilometers per hour. And remember, they both took off from their starting point at the exact same moment.
Moving to Section 2, Step 1, Finding Distances.
Now, the crucial point here is that we know their speeds and their directions. But obviously, speed isn't distance. If we want to know the actual physical gap between these two planes, how do we figure out where they literally are in the sky? Well, by multiplying their speeds by the 1.5 hours of flight time they've been in the air, we can actually map their physical locations. For plane 1, going 1,000 kilometers an hour for 1.5 hours means it's traveled 1,500 kilometers north. For plane 2, at 1,200 kilometers an hour, it's traveled 1,800 kilometers west. Boom. Now we have some tangible distances to work with.
Notice how these flight paths map out here. We've got our starting point right at O. Plane 1's path is line OA, stretching straight north. Plane 2's path is line OB, stretching straight west. And because north and west are exactly 90 degrees apart, this creates a perfect right-angled shape on our virtual map. It's like a giant puzzle piece right in the sky. The actual physical distance between the two planes right now is just that diagonal dotted line labeled AB.
Which brings us to part 3, the tool. Enter the Pythagorean theorem.
To bridge this physical gap between our two planes, represented by that line AB, we need to pull out a classic mathematical detective's tool. We have two known sides of a right triangle, right? And we need to solve for the longest side, the hypotenuse. This perfectly illustrates the Pythagorean theorem, which states that the square of our unknown distance, AB, equals the sum of the squares of their individual travel distances, OA and OB. Think about that for a second. It's a theorem developed thousands of years before the first airplane was ever even dreamt of, yet it is exactly what we need to track them today.
Section 4, Step 2, Calculating that separation.
So let's plug our specific real-world flight distances into this ancient Greek formula and just see how it all builds. Substituting our calculated distances from the map, we get AB squared equals 1,500 squared plus 1,800 squared. Now, obviously, we're looking for AB, the actual distance, but first we've got to deal with the squares of these honestly pretty massive numbers.
Part 5, Real-World Math in Action.
Okay, this is where the numbers start to look a little intimidating, but we can actually break the math down into really digestible steps so we don't just get completely lost in the millions. You don't actually need to multiply 1,500 by itself right out of the gate. Instead of doing all that heavy lifting straight away, we can just cleverly factor out the hundreds. Since both 1,500 and 1,800 are multiples of 100, we pull out 100 squared. That leaves us to simply square the much smaller numbers inside the parentheses, 15 and 18. And that's easy. 15 squared is 225, and 18 squared is 324. Add those together and you get 549. So this entire massive equation shrinks beautifully down to 100 squared times 549.
But wait, we can go one step further to simplify that 549. By factoring out a 9, it breaks down into 9 times 61. So our equation for AB squared is now 100 squared times 9 times 61. And you know what? This sets up the absolute perfect foundation to find the square root. Why? Because both 100 squared and 9 are perfect squares, completely ready to be cleanly extracted.
This final factored value gives the math such a satisfying payoff. By taking the square root of these parts, we mathematically prove exactly how far apart those two planes are in the sky. And it ends up being 300 times the square root of 61 kilometers. All of that using just their starting speeds and a really simple geometric triangle. How cool is that?
You know, it's incredibly empowering to see how this kind of fundamental math can track massive objects through the sky with such absolute precision. It literally transforms a complex logistical question into a super elegant equation.
Which leaves us with a pretty provocative thought. If a geometric rule discovered in antiquity is out there calculating modern jet flight paths, where else is an ancient Greek theorem working behind the scenes in your world today? Thanks so much for joining me for this explainer, and hey, keep your eyes open for all the hidden math around you.